All right, here in this video, I'm going to be giving you an introduction to thermochemistry. So thermochemistry, as the name implies, is talking about the chemistry and temperature. So we're really talking about temperature and heat transfer and energy temperature as it relates to chemistry. So all reactions involve energy in some form. And the most important thing about thinking about energy and temperature is that heat always flows from hot areas to cold areas. So you're really talking about the transformation of this energy, the flow of the heat from hot to cold. If something is getting hotter, something else must be getting colder at the same time. That's the energy flow. So imagine it this way. I thought about this morning as I was petting my own dog. If you pet a dog, dogs are warmer than humans. They have a higher body temperature. So if you pet a dog, your hand is going to get warmer. The energy is flowing from the dog's skin and its fur into your hand. So in return, the dog is going to get a little bit colder because the heat transferred from its skin and fur into your hand. You can also think about this like if you have really, really cold feet, you walk outside in the wintertime in the snow and your feet get really cold. And so then you go put them up against someone else who is really warm. Your feet are going to get warmer. They pull the energy, the heat transforms, and it flows from hot areas to cold areas. So whoever you put your really cold feet against is going to get colder in return. The heat flows from hot to cold. Okay, so now let's talk about this in relationship to chemistry. So this is really, really important right here. If a reaction gives off heat, then the surroundings get hot and the system or the reaction, I'm going to be using these terms interchangeably. System usually means the reaction itself. So if the reaction gives off heat, then the surroundings, everything else around it gets hot, and the reaction itself gets cold. So you can think about it this way. So we did a reaction in the lab in which you put some hydrochloric acid with magnesium. So this is one of my, I don't know if you know, but this is one of my favorite reactions, hydrochloric acid with magnesium. And what happens is it gets really hot. And so the reaction occurs between the magnesium and the chloride, and energy is transferred to the surroundings. So that means that your beaker gets hot, the air above it gets hot, the liquid solvent around it gets hot. So the reaction is just occurring between the magnesium and the hydrochloric acid. That's the reaction. Everything else around it is the surroundings. The glass of the beaker, the solvent, the air above it. All of that is the surroundings. So the reaction gave off heat. The surroundings got hot. This kind of reaction is called exothermic. You need to get this in your head. Exothermic means reaction gives off heat, surroundings get hot. Conversely, you have another kind of reaction in which a reaction requires heat. So, if the reaction requires heat, that means it must take in heat in order to occur, then the surroundings are going to get cold. That kind of reaction is endothermic. So a really good example of this is those cold packs that like traveling personal trainers use. So it's a pack, and then as soon as you crack it, some chemicals start to mix. Energy then is required for the reaction to occur, and the cold pack gets cold. That's the surroundings. The reaction is the mixing of the chemicals. It takes in heat from the surroundings, and the surroundings get cold. That kind of reaction is called endothermic. So again, you got to get this in your head. This is super, super important. Exo gives off heat, surroundings get hot. Endo requires heat, surroundings get cold. All right, so what exactly is energy? So a physicist might say that energy is the capacity to do work. As a chemist, I don't really like that. I don't think it really helps us. What work are we even talking about? So I prefer to think about energy chemically. So there are two kinds of energy. One is potential energy. Potential energy is the energy due to position. So the way physicists, again, usually talk about this, they talk about a waterfall. And right here at the tippy top is the water that's about to go over the waterfall. Well, it has a lot of potential energy because it's right at the top before it's about to fall. It has lots and lots and lots of energy here. So at the top of the waterfall, you have high amounts of potential energy. That's the energy due to position. A chemist would prefer to talk about chemical potential energy being stored in bonds. So in the bond between two atoms, there's a lot of potential energy stored there. Kinetic energy, on the other hand, is energy of movement. So again, going back to our very typical physicist example, we have our waterfall. We have a bunch of water here at the top of the waterfall about to go over the edge that has high potential energy. And then as the water falls and it crashes down to the bottom, all of this moving water has high kinetic energy. Lots and lots of movement that has high kinetic energy. So again, I'm a chemist, so I prefer to talk about things chemically. So to a chemist, kinetic energy really is the movement of molecules. Heat and energy causes molecules to move around more rapidly. And so what do you think? This is, if I were in class, this is where I would have you guys talk to me. You have a difference between a solid. So here's my example of a solid. Another example of a liquid. We have some water molecules moving around versus a gas. So my question for you would be, which one has the greatest amount of kinetic energy? The answer to that question is the gas. Gases have very, very high kinetic energy. They're moving around rapidly. Those gas particles are colliding with things. That's what it means to have energy of movement to a chemist. Very, very high kinetic energy. Over here, the solids would have the lowest amount of kinetic energy. There is some movement. It's not, again, you really don't stop molecular movement unless you're at absolute zero. So there is movement of the molecules even in a solid, but they're not moving very much. So they have very low kinetic energy. Liquids, of course, are in the middle. They have a middle amount of kinetic energy. There is some movement as the molecules slide past each other in the liquid state, but it's not nearly as much as if you were a gas. So solids, low energy. Gases, high energy. Liquids are in the middle. So there is this law of conservation of energy, just like the conservation of mass, how we use it to balance chemical equations. The law of conservation of energy tells us that energy is neither created nor destroyed. It is simply transformed. So during the reaction, so again, chemically thinking about this, during a reaction, the energy that is stored as potential energy in bonds is transformed into kinetic energy by heating up the surroundings. So again, we're just talking about transforming energy, transferring energy. We're not creating it or destroying it. As a reaction occurs, if it's exothermic means it releases heat into the surroundings get hot. That energy that's causing the surroundings to get hot comes from breaking of bonds. Energy that is stored as potential energy as bonds is released into the environment. Now this, I cannot stress enough. We're about to get mathy, and so we really need to watch the signs of your energy variables. You're in charge if something is positive or negative, and you really, really need to be super, super careful about what gets a positive sign and what gets a negative sign. It's a big deal. You need to know what your signs are. So we're going to be talking about energy as heat, and it's given the variable of lowercase q. And the sign is from the perspective of whatever you're talking about. I'll tell you what that means in just a second. So let's talk for a second about hot soup. Okay, so you've got a nice mug of hot soup. It's a cold day, and it's sitting there in its mug on the desktop. And again, we're talking about energy transfer. So the hot soup, if we left it there for a while, over time, I don't know, let's say that our hot soup is 100 degrees Celsius. Over time, our hot soup would no longer be hot anymore, right? If we let it sit there for, 20 minutes, it's going to lose energy, lose its heat, and we might come back and it's only 70 degrees Celsius. What we're talking about right now is that heat and energy flow. The hot soup sitting there on the bench top is going to be losing its heat to the surroundings. Again, the surroundings are the beaker it's sitting in, the mug, whatever, the bench top, the air above it. Those are the whole of the surroundings. So the hot soup loses its heat to its surroundings. So the Q of the soup is negative. It is losing heat, negative. The Q from the perspective of the surroundings is positive because the surroundings are gaining energy. They're heating up because the energy is transferring from the soup to the surroundings. So the Q of the soup is negative. The Q of the surroundings is positive. The soup lost energy as it cools. The surroundings gain that energy as they heat up. Here's another example. Ice melts. So you take an ice cube out of the freezer. That's my ice cube. And again, you put it down on a bench top. After some time, and this ice coming out of the freezer is about 0 degrees Celsius. Over time, we come back to it later, and all we've got is a puddle of water. That puddle of water is no longer 0 degrees Celsius. Maybe it's warmed up to 15 degrees Celsius. So the ice melts. So what is gaining energy? The ice cube is gaining energy. I told you that solids have low energy, liquids have higher energy. So the solid gains energy when it melts. So the Q of the ice is positive. It gained energy. Where did it get the energy from? It got energy from the surroundings. The surroundings then have a negative sign. The ice gains energy to melt, so the Q is positive. The surroundings, the air around it, the bench top, the energy flowed from there into the ice. So the Q of the surroundings is negative. So this is the summary. Ice is gaining energy. The surroundings are losing it. Q of the ice is positive. Q of the surroundings is negative. You have to watch these signs. It is so important. So another consequence of this energy transfer and heat flow is that the Q of the system is always equal in magnitude but opposite in direction, in sign. So negative Q of the soup is the same positive Q of the surroundings. All of the energy lost by the soup is equal to the amount of energy gained by the surroundings. So they are equal in magnitude to each other. The amount of energy transferred is the same, just the sign is different. When the ice melts, the energy gained by the ice is equal in magnitude, the same amount of energy, but opposite in sign to the surroundings. So let me put some numbers to this just so it makes sense. I'm going to be making these up. These aren't like real. So if we look at the ice melts, let's say that it takes 76 joules to melt ice, whatever quantity of ice we have. That means the surroundings lost 76 joules. So since the surroundings lost it, the Q of the ice is positive 76 joules, that's how much energy the ice gained. The Q of the surroundings is negative 76 joules, because that's how much energy it lost. Equal in magnitude, 76, opposite in sign, gain versus lost.